Welcome everybody to the third week second video lecture. So in this video lecture we will continue with our understanding of various proof techniques, particularly understanding of the proof by contradiction. We have started this particular technique in the last video lecture and will continue to study this by looking at more problems. So to recap, to prove a statement like A implies B, there are various different proof techniques. We have already seen proof techniques, namely constructive proof, proof by contradiction, and so on. We will be seeing much more other proof techniques also in the next 1 or 2 weeks. So one thing that I have always mentioned, and I repeat here again, if you ask which proof technique to apply to which problem, it depends on the problem. The answer of which proof technique should be applied depends on the problem. While for some of the problems, it can be split up into smaller problems that can be easily tractable, while for the many others, one can view the problem in a different way and that can make it easier. But which problem to split and how to split it and how to view it depends on yourself. This is an art in itself that has to be developed. You have to develop it. In this course, we will be giving you all the various tools that are there. We will give you thumb rules, but at the end, it's your skill that you have to develop, that you have to apply to find out which problem should be solved by which technique. To start with, we looked at some of the tricks that can be applied to solving problems. The first trick was splitting it into smaller problems, namely when to prove A implies B, B can be written as C and D. In that case, A implies B is same as proving A implies C and A implies D. We also saw that we can remove redundant assumptions, and by doing so we can make our problem simpler, which can be easier to handle. The third trick that we saw is that sometimes proving something stronger is easier, in the sense that if C implies B, it may be possible that A implies C is easier to prove than A implies B. But since C implies B, so A implies C is good enough for proving A implies B. We saw 3 applications of these 3 techniques in some in the video lectures last week. Other than these 3 small tricks, we also started looking at constructive proofs, or what we call as direct proofs. So there we had 2 different kind of constructive proofs. First of all, there was direct proof. The idea was to prove A implies B. You work with A and step by step prove B. Sometimes we saw that proving it in this way can be hard, so can be magical. So instead, one can come up with something called a backward proof. So backward proof is a simpler technique. The idea is that instead of starting from A and slowly massaging it to get B, you start from B. You start simplifying B. And if you can simplify B to something like C, then proving A implies B is same as proving A implies C. And proving A implies C can be an easier job because you have simplified B to get C. So this is the main thing of the direct proof. There was another kind of constructive proof that we looked at, namely what we called as the case study. So in this case, we split the assumptions into parts. So in other words, if A is written as C or D, then A implies B is same as saying C implies B and D implies B. And the main trick here is to split A into the two cases or three cases or whatever number of cases of C and D, such that C implies B and D implies B are easier to prove. So we saw examples of all these various techniques in our past video lectures. In the last video lecture, we started with this new proof technique called the proof by contradiction. So the idea here is that to prove A implies B, it is same as proving not A and B is false. So sometimes instead of proving A implies B, one can end up proving not A, not B and A is false. This technique is called proof by contradiction, or in other words, you view the problem in a different way. Instead of viewing the problem as A implies B, you view the problem as not B and A is false. A similar statement is what we call proof by contrapositive, which we will be doing in the next video lecture. So in the last class we saw application of this proof technique to solve a problem, namely to prove that there are infinitely many primes. In this video lecture we will also apply this particular proof technique of proof by contradiction to a new problem. But before we start on the problem, let's try to understand again what is the proof of contradiction all about. So it's like there are two different ways of proving that the earth is flat or earth is not flat, the earth is round. The first approach is a direct approach, namely saying that, oh, see, a ship is coming from the horizon. When it comes, we first see the top of this ship and slowly the whole complete ship. So the earth must be round, hence not flat. The other technique is to say that let's assume that the earth is flat. In that case, when the ship came from the horizon, the whole ship would have appeared at the same time. But that didn't happen. We first see the mast and then the whole ship. And that's the contradiction. The contradiction to the assumption that we have made, namely the earth is flat. As you can see that both the proof or both the statements are very similar. It is just in kind of the same difference in wording. But that's what the proof of contradiction is. Proof by contradiction, it just restates the problem in a different way, and in fact a proof by contradiction can very easily be converted into a direct proof. But sometimes getting a direct proof directly can be more complicated, and that is why we go through this thing called proof by contradiction. So now for today's video lecture, we will be working with numbers. Here we say that a real number is rational if it can be written as the ratio of two integers, namely p by q. For example, 1, 2, 3, all of them can be written as 1 by 1, 2 by 1, or 3 by 1, and 2 by 3, 49 by 99, and so on and so forth. The question is that can you prove that square root 3 is not a rational number? So namely, square root 3 cannot be written as p by q or a ratio of two integers. Now we prove it using contradiction. Let's see. So let us assume that square root 3 is rational, or in other words, square root 3 is equal to p by q. So that is the assumption. This is the contradiction part, right? This is the not b part. And now we have to prove that not b and a is false. And what is a here? A is everything else, all the things that we know of. So if square root 3 is equals to p by q, then do I get something weird statement? Now, to prove that we get some weird statements, or maybe we do get some false statements, we will do a kind of a case analysis. We will apply the case analysis technique here. But to understand it, let's first simplify it. When I write square root 3 as p by q, and if both p and q are divisible by 3, then I can just strike out 3 or divide both p and q by 3 and I get a smaller p and q. Right? It's like if by chance square root 3 is equals to 18 by 36, I could divide by 3 and get down to 6 by 12 or something like that. Of course, that is not true because this number is equals to half. But the idea is that I can always write, if square root 3 is a rational number, I can always write square root 3 as p by q, where both p and q are not divisible by 3. That means one of them can be divisible by 3, but not both of them. Both of them cannot be divisible by 3 at the same time. Now if that is the case, in any case, when I have square root 3 equals to p by q, this translates to, of course, 3, if I square both sides, 3 is equals to p square by q square, or in other words, 3q square is equals to p square. And that is where we will be drawing our contradiction. Okay, let's see. Let's do it case by case. So case 1, let's say that both p and q are not divisible by 3. That is, neither p nor q is divisible by 3. Then can 3q square be equal to p square? Right? That is the first case. The second case will be if p is not divisible by 3 and q is divisible by 3. And third case will be if p is divisible by 3 and q is not divisible by 3. Note that these are the only 3 cases, because the fourth case would have been p and q are both divisible by 3, and in that case we would have got a smaller p and q, as we just now argued. So if you can prove that in all the 3 cases we can get a contradiction, namely we can prove that 3pq square cannot be equal to 3p square, then we are fine. So if all these cases we prove that 3q square equals to p square is not a possibility, then we get a contradiction. Now let's do it by case. Let's consider the first case. First case when both p and q are not divisible by 3. So in that case, 3p square or 3q square is of course divisible by 3. That we know, because 3q square has a 3 in it. But p square is not divisible by 3, because p is not divisible by 3. So if p square is not divisible by 3, but 3q square is divisible by 3, then can p square be equal to 3q square? Of course not. So 3q square cannot be equal to p square, in this case 1. Now let's go to the case 2. This is the case where p is not divisible by 3, but q is divisible by 3. Again, the same argument, 3pq square is divisible by 3, and p is not divisible by 3, therefore p square is not divisible by 3, and hence 3pq square cannot be equal to p square. Now let's see the third case, namely, if p is divisible by 3 and q is not divisible by 3. Now p is divisible by 3, that means p square is divisible by 3. And on the other hand, 3q square is also divisible by 3. So that argument will not work. So what should we do? Let's see. Say p is equals to 3 times k, because p is divisible by 3. Right? So 3q square equals to p square is same as 3q square equals to 3 times k whole square, because I assume that p is equals to k. So 3q square equals to 9k square, which is same as q square equals to 3k square. Right? Now 3k square is of course divisible by 3, because 3k square has a 3 in it. But q is not divisible by 3, so q square is not divisible by 3. And hence, by almost the same kind of argument, 3k square cannot be equals to q square. Thus, even in this case, square root 3 cannot be equals to p by q. Or in other words, 3q square cannot be equals to t square. Thus, to wrapping up the whole proof, we prove by contradiction. We assume that square root 3 is equal to p by q, which is the opposite of what we have to prove. And then we assume that p and q has no common factor, else you can factor it out. So in other words, we can assume that both p and q cannot be divisible by 3. And now since square root 3 equals to p by q, or in other words 3q square is equals to p square, we say that we do a case-by-case analysis and prove that this cannot be true. 3q square cannot be equal to p square for any integer p and q. And hence we get a contradiction. So this is an example where we not only apply the proof of contradiction but also the case study proof into it. Now there are lots of similar problems that can be asked. Particularly leave this following 3 problems as a practice problem. Namely, prove that square root 2, square root 5 and square root 6 are not rational numbers. So none of these 3 are rational. Now I would also like you guys to solve some more statements or observations about rational numbers. Namely, here are they. Prove that a rational times a rational is a rational number. A rational times a non-rational is non-rational number. For example, since square root 3 is not rational and minus 1 is rational, so minus square root 3 is not rational. 1 by rational number is rational. 1 by a not rational number is not rational. Therefore, even 1 by square root 3 is also not rational. And what about not rational times not rational? Is it rational or not? I leave it to you for you guys to check it out. Is the product of two non-rational numbers non-rational or rational? Now moving on, let me prove one more thing. Namely, what about if I add two non-rational numbers or something like that? So is square root 2 plus square root 3 rational? We have proved that square root 3 is not rational, and I have asked you to prove that square root 2 is not rational. But what about square root 3 plus square root 2? Let's prove that it is not rational, right? So the proof is again by contradiction, and here is it. So say let square root 2 plus square root 3 be a rational number. That is, square root 2 plus square root 3 is p by q for some positive integer p and q. So therefore square root 2 plus square root 3 equals p by q, which means that square root 3 is p by q minus square root 2. If I square both sides, what do I get? I get 3 is equals to p square by q square minus twice square root 2p by q plus 2. Which means if I just move these things around, we get twice square root 2p by q is equals to p square minus q square by q square. And therefore square root 2 is equals to p square minus q square by 2pq. Now since p and q are integers, so p square minus q square is also an integer, let it be p prime, and 2pq is also an integer, let's call it pq prime. So in other words, if square root 2 plus square root 3 is a rational number, I end up proving that square root 2 is a rational number, which is something that I will know to be false. Right? So, in other words, if square root 2 plus square root 3 is a rational number, then square root 2 is a rational number, which is a contradiction. So our initial assumption was wrong, that is square root 2 plus square root 3 is not a rational number. Now I ask you guys to repeat the same proof, where instead of assuming that you know the proof of square root 2 is not rational, you really use the fact that square root 3 is not rational, which is what we have proved till now. So this brings us to the end of the video lecture. In the next video lecture, we will be talking about proof by controversy.